All right. So, welcome back to another fun-filled day of trig. I'm going to start with the usual questions. How's the homework going? Any questions on what we've talked about so far? All right, hearing and seeing none. I'm going to assume everything's going okay. Hopefully you're liking this turn for where we're going. We're getting away from the identities, ish. I mean, we're still going to use the identities, but we're not concentrating on the identities. And we're going to start actually using these trig functions for what they were designed for. So where we got last time, we started solving equations, and we saw that there was a specific process, right? We needed to find um, all of the solutions in within one period and then add on the multiples of the period to catch all the possibilities. So I want to kind of refresh your memory. We'll do a quick example of one, and then we'll go into some new things. We'll talk about how we can use our calculator to help us. And then we'll talk about what happens when these equations get a little bit nastier, because the ones we've seen so far are pretty simple, right? I think even you guys can admit that in terms of what equations could look like. So let me go to the board. Um, all right, so let's go to the board and let's look at an example of what we were talking about last time. So pretty standard, except I want to go to one of the non-big three. So let's try this. Let's say we have the secant of theta is equal to negative square root of 2. So just like any equation, we're trying to find the thetas, the angles that we can put in here so that we get truth. So we're looking for any angle whose secant is negative root 2. All right, so that's easy enough. Let's look at our chart. And remember, what we need to do is find all of the solutions in one period of secant. Secant, of course, has a period of 2 pi. So we're going to look between 0 and 2 pi. So if we look at our chart, go down the secant column, the first one we're going to see is theta equals 3 pi over 4. So we know that 3 pi over 4 is one of the places where secant is equal to minus root 2. And then if we continue looking down our chart, we go a little bit further. We're going to see another place is 5 pi over 4. And those are the only ones between 0 and 2 pi. All right, so we just caught all of them that are within one period. So then what we're going to do is we're going to add on to each one of these a 2 pi n, because that 2 pi n, that's catching now all the coterminal angles, or even better, they are coterminal in terms of secant. But if we kind of want to think about this generally, these are all of the angles that are periodic with 3 pi over 4. So they're the ones that show up in the same location in the periods as we copy. So we found all the solutions within one period, and then we added multiples of the period. So hopefully you guys remember that, seeing things like this, and this is going to be our process. But unfortunately, we don't always get nice values. Like every value I've given you with the respective trig function, they've been ones that are on our list, right? That we can actually calculate. So the question is, what if we had something like this? What if instead we had something like sine of theta equals negative 0.1? All right, so if we've got sine of theta equals negative 0.1, it's the same question. Question is, what angle gives us a sine of minus 0.1? but that's not on our list. You go down our chart, our special angles, there isn't one that does this. However, there are angles that will give us a sine of negative 0.1. I know this because this number is between plus and minus 1, and we saw that with sine, its range is from -1 to 1, so there will be something that works. Okay, so what do you guys think? How are we going to be able to answer this? Okay, so Amber just said calculator with the question mark. Yep, absolutely. We're going to need to use a calculator or a computer or something like that. But what are we going to use on the calculator? What command? So Adam just put in inverse with the question mark. And that's absolutely right. We are going to use inverse sine. That was the whole point of the inverse trig functions. We developed those so that we could figure out angles that give us the specific trig values. So what we're going to be able to do is use inverse sine. And so one of our solutions is most definitely going to be inverse sine of minus 0.1. Right? There will be an angle that this gives me, and it is an angle whose sine is negative 0.1. All right, but now the question is, are there more in one period of sine that will do the same thing? And the answer to that is yes. We definitely have more, because let's think about sine. And let's think about what we're looking for. We're looking for an angle that gives us a negative sine. So where can that happen? Which quadrants give us negative sine? All right, thanks, Diego. He just says 3 and 4. So definitely 3 and 4. So there are two locations where there's going to be a theta, gives us a negative 0.1. So let me draw a picture of the unit circle up above, and let's talk about where we're looking here. So here's our unit circle. So we need a sine of negative 0.1. So the quadrant 3 angle is going to be somewhere down here. And the quadrant 4 angle, symmetry, is going to be over there. And this theta, the one that inverse sine is telling us, is one of those two. Which one? Is it the quadrant 3 or quadrant 4 angle? All right, thanks, Diego. He just says quadrant 4, and that is correct. It is quadrant 4 because of the restriction on sine that we had to put in place for the inverse. So hopefully you kind of remember that that happened. If you don't remember exactly what it is, we know that with sine inverse, those angles are between minus pi over 2 and pi over 2. So minus pi over 2 is straight down, pi over 2 is straight up. So inverse sine gives us something in either quadrant 4 or quadrant 1. This one's going to be quadrant 4 because it's negative. Okay, so I'm going to put a check mark over here because that's the one that we just found with inverse sine. All right, so now the question is, how do we find the one in the third quadrant? All right, and a couple of you are chatting. Reference angle, absolutely. right? Now we're going to find the reference angle, and we're going to backtrack to find out what this guy is. All right, well, let's get a number for this. Let's get a decimal approximation, because I know you want that anyway. I left this here, and you are probably really uncomfortable with that. I will just tell you that to a mathematician, this is the angle. If we go to inverse sine and we use the calculator, that's going to give us an approximate. It's going to be a good approximate, but it's an approximate angle. Make sure that you know which mode you're in, whether you're radians or degrees. I'm going to stick with radians. And so what I get with my calculator is that this is approximately negative 0.1000167. How about I'll take it out that far? I figure 3 or 6 decimal places should probably be sufficient. Okay, so this negative 0.00 whatever, that's the rotation if we go clockwise to get us down there. All right. So then what's the reference angle? What's the reference angle for this one? Okay, so I'm getting some, what we're getting, Diego and Adam just put in like pi plus the 0.00167. That will get us this angle. The reference angle itself is just the positive of this. But you guys are correct that if we want to find the angle down here, we're going to need to take that and add pi to it. So here's our second reference angle, or sorry, not our second reference angle, our second angle. It's going to be approximately, so if I'll take pi and then add to it that 0.100167 blah, 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 I get approximately 3.24176. There's a whole bunch of zeros after that. But that's this angle that's in the third quadrant. Okay, so we now found all of the angles that occur in one period. And so just like before, we can add on our plus 2 pi n. I'll go ahead and put it up here as well. So let me just sort of differentiate between these things. The ones I circle in red, this is exact, right? That's the exact angle. That is the answer. That's this one in the fourth quadrant, plus all of those that are coterminal to it. These other two, these are approximate. So just realize that there is a difference. If you're going to be using this out in the real world for something, like we get an equation that tells us sine of theta equals minus 0.1, like we're trying to, maybe we're trying to measure how far a pendulum is moving or something like that, right? We need to use some trig. Then in that case, we definitely are going to be good with the approximate values. Okay, we're going to say, yeah, that's fine. But to a mathematician, those are not the angles. The angles are these. So you might be wondering then, how can we figure out the exact value for the one in the third quadrant? Just humor me. I know none of you are actually wondering how to do that. But if you wanted to figure it out, you would do the same thing as always. Think about what or how we found this with the approximate. And when I put it in the chat, a couple of you said, oh, well, let's just take pi and add that value. Well, that's what we would do to get the exact value. That one exactly would be pi minus sine inverse of negative 0.1. And then we put on our plus 2 pi n. And I know some of you might be going, wait a minute, why are you subtracting when before we added? Well, remember the inverse sine gave us a negative number. And so if I want to add, I have to subtract that negative number. So this would be the exact value for the ones that are in the third quadrant. So if that little bit just kind of went over your head, don't stress too much about it, because more importantly, when we're in this sort of situation, is using our calculator to get these values. And I'm pretty sure that the homework sets, when they ask you to do these, they're going to ask you to get decimals to a certain number of spots, right? They'll say, you know, enter a number to good to 5 decimal places or whatever. And you can use your technology, your computer, or your calculator, or your phone, or whatever it happens to be, to get that decimal approximation. All right, so a little more complicated, but not really, because we don't have to remember anything. We just use our calculator, we get these values, and then once we've got our angle, we can add our 2 pi in. All right, so for relatively nice trig equations, this is all you have to do. But if you look at all the ones we've done so far, the 2 I showed you today, the handful we did last time, they're all sine of theta equals, tangent theta equals, cosine theta equals. They're all really, really nice form. We have to allow for things a bit, that are a bit more complicated. And so we need to be able to deal with things that look uglier. So let me give you some examples of what I'm going to talk about next. Is what if instead of just theta, what if we had something like cosine of 2 theta equals negative root 2 over 2? Or the cotangent of 3 theta minus pi over 6 is equal to root 3 over 3. Or, and I think you start seeing what I'm talking about, is what if what's inside those trig functions is more complicated than just theta or just x? The question is, how do we go about solving these? Well, here's the good news. We don't really do anything differently. We're still going to try to figure out, like in this first case, angles whose cosine is minus root 2 over 2. Or in the second case, angles whose cotangent is root 3 over 3. So we're going to start the same way. But then this is where things change a little bit. So let's take that first one, cosine of 2 theta equals minus root 2 over 2, and let's solve that. Now let me show you how we're going to approach this. So the first thing I'm going to do, and this isn't necessary, but I'm going to do it just so you can kind of see why we're going to do the same steps. Let me, instead of having 2 theta there, let me replace it, say, with x. Okay, so x is going to equal 2 theta. That turns this thing into cosine of x equals minus root 2 over 2. And if I had presented you with this equation, you probably would have been happy-ish, right? You got, oh, that's not that big of a deal. I just have to find the angles whose cosine is minus root 2 over 2, and then add my 2 pi n's and all that. So let's solve this one. Let's find the angles where x is minus root 2 over 2. So where is that? Where's cosine equal to negative root 2 over 2? No worries, Adam. He just typed in 2 pi over 3, and then he went, no, wait, over 4. It's a typo. Okay, so turns out we found these exact angles just in our last question. Or sorry, not the one with the sine, but the one before that where we had the secant was equal to -√2. It's the same angle. So we're going to get here x is equal to 3 pi over 4, and x is equal to 5 pi over 4. So those are the two places where cosine is -√2/2. And then, of course, we have to add on our plus 2 pi n. So had it been just cosine of x equals, we'd be done. But we're not, because of that substitution. So remember how we said, let's let x equal 2 theta? Well, we have to put that back. And when we do that, if we replace that back in right here for x, we're going to get 2 theta equals 3 pi over 4 plus 2 pi n. That's for this one. And then for the other one, we're going to get 2 theta equals 5 pi over 4 plus 2 pi n. And you're not actually done with this until you get your letter all by itself. So we need theta equals, which in this case means we need to divide by 2. So if I just take everything here and divide it by 2, I'm going to do the same thing in this other equation. What I end up with is that theta is equal to 3 pi over 8 plus pi n. So 3 pi over 4 when I divide it by 2 gives me 3 pi over 8. And then the 2's cancel in the second piece, which leaves me just the pi n. And then similarly, the second one is going to give me 5 pi over 8 plus pi n. So really, there's just one more step with this. We still found the angles, found all the angles that make that trig function, in this case cosine, equal -√2/2. And then we just had to make sure that we saw that the angle itself was 2 theta. So we let 2 theta equal those numbers. And so our last step is now solve for theta. So there's the list. There's the list of all the solutions to this equation, right? Now, if you wanted to find them all, just start listing them out. Now what we're going to do is instead of adding 2 pi, we're going to add pi because things have been adjusted a little bit. So like this is what that list would be. If I just said, here's the list of thetas. Obviously, I can't write it forever, but we would get, say, 3 pi over 8. The next one when I add pi would be 11 pi over 8. Another pi would be 19 pi over 8. 27 pi over 8. ... So that'd be from that first list. The second list, we get 5 pi over 8. Adding pi gives me 13 pi over 8, and then 21 pi over 8. And I'm already tired of writing these. Right? But there would be the list of all the different angles. So again, if I said, hey, I need to know all the ones that are between pi and 3 pi, for example, then I would look at my list and figure out which those are. All right, so if what's inside is not just plain old theta or x, basically just do the substitution, still find out what those angles need to be, but then rewrite them and solve for your theta or your x. All right, so any questions on this one before I show you another example? Oh, we're good? Okay, so let's look at that other one that I had put up. And it looks something like cotangent of 3x minus pi over 6 equals √3/3. I think maybe when I wrote it up originally, it had a theta instead of an x, but that doesn't matter, right? Variable names don't matter whatsoever. All right, so here's what we're going to do. We need to figure out where is cotangent equal to root 3 over 3. So some good news for you. First of all, you can look on our chart and you can find that angle. It's a nice value. Where's cotangent equal to root 3 over 3? All right, pi over 3, good. A couple of you threw that in the chat window. All right, so what I know is that this angle, 3x minus pi over 6, that's going to have to equal pi over 3. So when I do this, I don't bother writing the theta equals and then do the substitution. I just jump straight to the, well, whatever this angle is, 3x minus pi over 6, it has to equal pi over 3. Okay, now Amber just put in 4 pi over 3 because there's another place that we see that the cotangent is equal to pi over 3. But I'm not going to worry about that one, because what we need to look for again are all of the solutions in one period and then add multiples of that period. And cotangent, since its period is pi, we only have to find numbers between 0 and pi that work. So this is the one and only angle between 0 and pi where cotangent is root 3 over 3. And so then what I'm going to add on to it is pi times n. And it's only pi times n because the period is pi. The period of cotangent is pi, not 2 pi. But notice that if n equals 1, then we're going to get 4 pi over 3, which is that other angle on our list. And this definitely catches all of them. So tangent and cotangent, you're going to like a little bit better. Well, okay. You should like a little bit better because there are fewer angles you have to find. You're going to not like tangent and cotangent because you're going to forget. And so you're going to go and find them all and add your plus 2 pi n's, and you're going to do extra work. All right, but it turns out cotangent and tangent are nice when it comes to solving equations because there's less stuff you have to do. All right, well, we still have to solve for x. We have to figure out what does x actually equal. Well, now this is like any other equation. We're just going to go ahead and move things around, and we're going to solve for x. So think about solving for x. Our next step would be to add pi over 6. So let's add pi over 6 to both sides. So that's going to give us 3x. If we take pi over 3 and pi over 6 and add them, that's if we get a common denominator, this is 2 6 plus 1 6, which is 3 6, which is also known as pi over 2. So we have pi over 2 plus pi n. All right, and then our last step is to go ahead and divide by 3. So we got to divide everything by 3. And we get x equals pi over 6 plus pi over 3 times n. And there's the list of all of the solutions to that original equation. If you let x equal any of these numbers, you will get truth. So again, if you wanted to see the list, you wanted to see what these numbers actually are, well, the first one would be pi over 6. Well, when I say first one, I mean the first one before we start plugging in n's, because there are smaller ones, right? The next one, if I would add 1/3 of a pi, that's going to give me pi over 2. Then I'm going to get 5 pi over 6, 7 pi over 6. The next one's going to be 9 pi over 6, which is the same as 3 pi over 2, and so on. If I went the other direction, I could have a negative pi over 6 if I subtract pi over 3, and so on and so forth. So there's the list of all the different numbers written out. But again, we can be nice and concise, nice and lazy, and just write it like I have circled in the black. All right, so if the stuff inside gets more complicated, don't freak out. Do like you normally do, but then set the inside equal to this. You guys have probably already figured out, now that you've been with me a while, that I like to use words like stuff and things, and I'm not really a big math technical guy. And the same thing holds here. What I'll often do is I'll like cover this up, and I'll say, okay, we need cotangent of hand to be √3 over 3. Well, that means hand has to be pi over 3 plus pi n. Or fist, cotangent of fist is √3 over 3, or the cotangent of this stuff is. And basically, I'm doing my substitution. I'm just naming it hand, stuff, fist, instead of u, theta, or something like that. Anyway, so just figure out what that stuff is, what that stuff has to equal, and then you go solve for your x. All right, so far so good. Any questions? Because we're not done. There's more we need to do when it comes to actually talking about solving equations, because they can get even nastier yet. And I know what you're thinking, oh good Lord, they get nastier than this? Well, yeah, they require us to do other things before we even attack this. So let me show you some examples of what I'm talking about, and then we'll talk about what our general strategy is going to be. All right, so here's an example of one that's going to require us to do something before we actually solve for angle. So let's say we've got tangent of theta times the cosine of theta minus the cosine of theta equals 0. Now this one's a little bit different, obviously. And probably one of the first things that you see, you should notice, is that we don't have just one trig function, right? Like all the examples we've seen so far has just had cosine or just sine or just secant or something like that. Now we've got tangent and we have cosine. Okay, well, when we're in that kind of situation, we have to do one of two things. Okay, and so here are basically what our goals are going to be. One is we need to make it so that we have only one trig function. Okay, so I just wrote make it so that only one trig function is present. If we're going to do that, this is going to require us to use identities. So you remember when we had those identities that would be like big and ugly and nasty, and then we simplified it down to just like one trig function? That's what we're talking about here, is that possibly by using trig identities, we can get it so that we have only one trig function. We only have sine, or we only have tangent, or whatever. So that's going to be one of our options. Another option is going to be to use algebra. And basically what we're going to do is we're going to use algebra to turn it into a different form. And that different form is going to be one that works better for us, that we can solve easier. And this, step number 2, you've done this before. You've totally done this before, where you've taken equations that were ugly or worse. You've done some algebra to simplify them. Things like when you had a log equation and you converted it to exponential form, and next thing you know, you could solve it. Or you had a polynomial and you factored, and that created equations that were easier. Okay, so you've done this before. Okay, so just some things to remember that might show up here. One of the big ones is factoring. We're going to do a lot of factoring. And I just want to remind you about fraction stuff. Because when we have fractions, especially fractions that we're adding or subtracting, we're going to want to combine them into one fraction, because sometimes that helps it get into a better form for us to solve. So algebra is going to be your friend here. It's going to take some of these equations and make it so that they're not as complicated and easier to solve. And the same thing is true about your identities. Your identities are going to change the form as well. Sometimes it'll get it just into terms of one trig function, or other times it might get it to an algebraic form that we can now handle, like factoring or something along those lines. Okay, so let me show you what I mean with this first equation. So the one I got written up here, tangent times cosine minus cosine equals 0. So this is one where factoring is totally going to help us. Notice that each of these terms has a cosine in them, which means if we factor that out, what we're going to see is something that looks like this. It's going to be cosine of theta times tangent of theta minus 1 equals 0. Right? Divide that first term by cosine and you're left with tangent. The second term, you divide it by cosine and you're left with 1. Okay, so we factored. And then, of course, you look at that and you go, okay, so what? But the so what here is when you have factors that multiply together to equal 0, we know that either one factor equals 0 or the other factor equals 0. So that's the 0 factor property. And notice what just happened was we started with one equation that was kind of big and ugly. We weren't really sure what to do with it. And now we're down to 2 equations, and each one of them is pretty easy. Right? This one, cosine theta equals 0. That's exactly the form that we've been playing with. We're looking for where does cosine equal 0. This second one, tangent theta minus 1 equals 0. It's not quite perfect. Really, all I want to do is move that 1 to the other side, but I can do that. I can add it. But now this one says tangent theta equals 1. Well, again, we know exactly what to do with that. So factoring brought us to a form where we had equations that were doable. So let's get our answers. So let's start cosine equaling 0. So what angle gives us a cosine of 0? All right, thanks, Amber. She just said pi over 2. So that's one of those. So I'm going to put here pi over 2 and then plus 2 pi n. And it's 2 pi n because cosine has a period of 2 pi. Anywhere else where we have a 0 for cosine in that single period? should see one on your chart. All right, thanks, Mariola, and Amber just threw in as well. 3 pi over 2 is our other option. So those are the two different possibilities from 0 to 2 pi. And again, so we're going to add plus 2 pi n to each. All right, so those are angles that will make our original equation equal 0 because they make cosine equal 0. All right, but we also have tangent can equal 1. So where does tangent equal 1? All right, thanks, Mariola. She says pi over 4. And again, tangent. Remember tangent. We only have to look between 0 and pi. So pi over 4 is the only one that works between 0 and pi. So then we add on to that pi n. And it's pi times n because the period of theta is pi. All right, so there's the list. There's the list of all the angles that will make that original equation true. So let's just start with the small, let's go positive angles, and let's just look at this, make a list. So we're going to get pi over 4. The next one's going to be pi over 2. Then we're going to get 3 pi over 4, or no, sorry, I lied, not 3 pi over 4, 5 pi over 4. And then we're going to get 3 pi over 2, and the list would continue. The next one after that, I believe, would be 9 pi over 4. Yeah, 9 pi over 4 would be the next one, and so on and so forth. All right, so kind of see how factoring can help us. We'll do another one, but factoring is definitely your friend when it comes to solving trig equations, especially when we've got more than one different trig function.
Actually, Bruce, I have a question. Isn't cosine limited to 1 and 2? So why would 3 pi over 2 be part of this?
So cosine, okay. Inverse cosine is restricted to just quadrants 1 and 2. But this is sort of the same argument that we had with, remember that one we did with the calculator, the sine of minus 0.1 or whatever?
Yeah.
We did inverse sine to find one of the angles, but then we had to use our geometry to find the other. And that's kind of the same deal. Inverse cosine would give you pi over 2. However, we know that 3 pi over 2 also works just from the symmetry of the circle.
So then why wouldn't you include tangent in sector or quadrant 3 then? Why do we limit it to only 1? Wouldn't it be the same in quadrant 3?
Okay, so yes, it is also there in quadrant 3, and that's going to be caught by n equals 1.
Oh, yep. Okay, cool.
Because again, we're using the periods. And when it comes to tangent and cotangent, you don't have to worry about the full circle anymore. You only have to worry about half of the circle.
Yeah, I'm remembering that from last class now.
Okay.
Mm-hmm.
Cool.
Thanks.
All right, any other questions on this one? But that's a good question, Adam. I'm sure other people were probably curious or had similar thoughts. All right, well, let's try this one. Let's say we've got sine squared x plus sine of x minus 2 equals 0. Now, for this one, we see that it already is just in terms of one trig function, right? All we have is sine. So that's good. However, yeah, but there's a sine squared. Well, this is another one that we want to factor. This is quadratic form. If we were to say let u equal sine of x, then this would look like u squared plus u minus 2. So it's quadratic form, and since this one's quadratic, we can look to see if it factors. And it does. This will factor to u plus 2 and u minus 1. So what we know is that u is either going to equal -2 or u is going to equal 1. So let's back substitute. Let's get rid of those u's because I don't really care about the u's. I know u is equal to sine. So basically we're looking at where does sine of x equal -2 and where does sine of x equal 1. So you may remember quadratic form, seeing that kind of stuff back in some point in algebra. This is another place where we want to make use of it. But now we can go ahead and solve. All right, so let's start with this first one. Where does sine of x equal -2? So look on your chart, and where do you see sine equaling -2? And this is horrible. I mean, it's not on our chart. If you look down that sine column, you never see it equal -2. Okay. Okay, so William, you just said that you see that cosecant gives it to you at 7 pi over 6. And yeah, if this had been cosecant x equals -2, then 7 pi over 6 would be a totally good answer. But sine itself, if you look down that column of sine, you never see -2. Okay, well, let's come back to that. How about sine equaling 1? Because that is on your chart. Where does sine equal 1? All right, Amber just gave me pi over 2. Beauty. So we'll put pi over 2, and then, of course, add 2 pi n. Anywhere else where sine equals 1? So if you look down that chart, you shouldn't see any other ones. Okay, so there's the list for sine of x equals 1. We got that. We're good. Okay, so let's go back to sine equaling -2. So since it's not on our chart, what are we going to do? All right, calculator. Eris just said, let's go calculator. All right, do inverse sine. Let's do inverse sine of -2. Because that's the whole point, again, of the inverse trig functions, right? So we go, okay, well, let's go with inverse sine of -2. So if you've got your calculator handy, so Amber just said error. That your calculator just said error. Yeah, all right. Anybody else having any luck? So Devin, you're also saying no luck. All right, so doesn't exist? Yeah, turns out that no, you cannot have a sine equaling -2. Okay, so the answer to this is cannot happen. Hold on one second. So here's where Math Lawyer has to come in. This can happen, but only if you have complex numbers and complex angles, but we don't want to do that, okay? All right, so this can happen if you have complex numbers. So William, when you said you got a decimal plus a decimal, it was giving you the complex number. So this actually can't happen if we're going to allow only real angles. All right. It would have been nice if we didn't have to go through the whole, try to do the calculator and do all that. And it is possible for us to have recognized that at the start. Think about the range of sine. What's the range of sine for real values? What numbers come out of sine? All right, thank you, Amber. She just said from -1 to 1. Okay, so the range is -1 to 1. This is outside the range. That's outside the range, which is why you got an error on your calculator, right? And Williams has got a number because he's got a calculator that's smart enough to know that you can have complex angles. Okay, so watch out for this, because sometimes when we do the algebra, we will get numbers that are not in the range of their respective functions. So this is why we care about range. It's not just for the hell of it. There's a real reason we got to watch out for it. All right, so let's come back to this question then. What are the solutions? Well, we definitely saw values that made sine equal 1. We didn't see any that made sine equal -2. So it turns out that our only solutions were these that made sine of x equal 1. So if you ever run into this, where you get something that just can't occur, just ignore it. It's not part of the solution. It doesn't mean there's no solution. It just means that that piece isn't adding to the solution set. So we still go ahead and find the solution sets from the other pieces and call it good. All right, so any further questions on that? Okay, so seeing and hearing none. Let's move on to the, what about identities? How can we use identities to help us when we get these kinds of equations? Now, in terms of where they're going to be useful, it really depends. It depends on what these things will look like. But I'm going to start with one where we're going to change it so that everything is just in terms of one trig function. So let's look at this, where we have 2 sine of x plus cotangent of x is equal to cosecant of x. And if you were to look at this and think about trying to do something with algebra, I think you might struggle, because it definitely doesn't look like there's any kind of factoring or any kind of fraction stuff or anything like that. So at this point, you'd probably feel like you're a little bit, screwed. So let's instead try to use identities to turn this into just one trig function. So I'm actually going to start with the cotangent and cosecant. Let's turn those into sines and cosines, so that this looks now like 2 sine of x plus cosine over sine equals 1 over sine. So I just use the quotient identity for cotangent and the reciprocal identity for cosecant. Which actually reminds me, I did put up an identity sheet onto the Canvas site. I think it was Amber who asked me if I would do that. So there should be one up there. It is 2 pages long. It's front and back. That is a PDF file. Then I've got them sorted by all the different forms. So feel free to look at that and print it out for your reference. You know, use it for exams or whatever. But anyway, all right. So here we are. At least now we're down to 2 trig functions. It's only sine and cosine, which I think is definitely more helpful. All right, but I still want to see if I can replace further. Before I do that, though, let's clear these fractions. Let's just do an algebra step real quick. Let's multiply both sides by sine. So that will turn this into 2 sine squared plus cosine is equal to 1. So those fractions no longer have denominators. We've canceled those fractions out at a cost of making a sine squared. All right, so I actually like the look of this a lot better than what we started with. It's a nicer form. But I'm still not down to just 1 trig function. But do you see a way that we could make it just 1 trig function? Okay, so William, you're saying let's write it as 1 minus cosine, move the cosine over. The problem with that is we still have cosine and sine, they're just in different spots of the equation. We didn't actually get rid of one of them. Okay, so then Amber suggested maybe power reduction. We've got sine squared, we could definitely use power reduction on that. Era's just said 1 over sine. 1 over sine is probably not going to be that useful because that's just going to give us a cosecant. I don't think I want to do power reduction, but I definitely want to do something with the sine squared. What I'd love to do is turn it into something with maybe cosine. What identity do you know that involves sine squared and cosine? All right, thanks, Diego. Just put in Pythagorean. How about we use the Pythagorean? We know sine squared plus cosine squared is equal to 1. So let me just write that here real quick just to remind you this what we're using. So we got sine squared plus cosine squared equals 1, which means sine squared, that's going to equal 1 minus cosine squared. And if we put that in for the sine squared, this becomes 2 times 1 minus cosine squared plus cosine equals 1. And now we've got just cosine. So check out what happens. If I distribute, I'm going to get 2 minus 2 cosine squared plus cosine x equals 1. I can move everything to one side, and now this is another quadratic. This is going to be minus 2 cosine squared plus cosine plus 1 equals 0. That plus 1 came from subtracting the 1, so 2 minus 1 is 1. So this is actually very similar to the one we just did. Instead of sines, now we have cosines. But this is one that we can factor, or at least we can attempt to factor. To help you see that, if you want, change this to like minus 2u squared plus u plus 1, and that might help you see the factoring. But I'm going to go ahead and jump straight to the factoring up here. So if you factor that, you're going to get minus 2 cosine of x, or sorry, 2 cosine of x plus 1 times minus cosine of x plus 1. or 2u plus 1 times minus u plus 1. But now that it's factored, we can set those factors equal to 0. So we'll get 2 cosine of x plus 1 equals 0, minus cosine of x plus 1 equals 0. And each of these I can solve for their respective values of cosine. So the first one's going to give me cosine of x equals minus 1/2. And the second one's going to give me cosine of x equals 1. And now we're back to business as usual. So let's look and see where cosine equals minus 1/2. So if you look on your chart, you'll see 2 places. The second quadrant angle is 2 pi over 3. The third quadrant angle is 4 pi over 3. And again, I'm going to put plus 2 pi in on each one of those. So those are the places where cosine is minus 1/2. And then cosine equaling 1, there's only one place that happens. That's at 0. And we can add 2 pi into that. But just so you know, if I ever had that, I wouldn't actually write 0 plus, because what's the point of having 0? I would just write x equals 2 pi n. So in terms of our solution set then, it's all of these angles. So the first pair, those are the ones that make cosine equal minus 1/2. And the second one is where cosine is equal to 1. But those are all angles that if we go back to the very original equation, we'll make it 0. Okay, so Diego, yes, you are correct that 2 pi would also make it equal 0. But that 2 pi, that's what we would find if we let n equal 1. 0 and 2 pi, since they're coterminal, you only need one of those, because the next one's in the next period. Does that answer that question for you? Yep, okay, good. All right, so you're starting to see why we care about identities. This one, without identities, would have been really, really difficult to solve, but we have them, and they are tools that we're going to use to help us solve these equations. So real quick, while I'm thinking about it, I want to give you guys the word of the day. Just popped into my head. So I think today's word of the day, again going with just things I happen to have handy, is going to be nut. I've got some walnuts here, so nut is the word of today. Nut, N-U-T. All right, so go ahead and write that down. Make sure you got it. I will write it down myself. But today, the word of the day is nut. All right, so let's look at another one of these. Let's take another equation where using identity is going to help us. All right, so let's look at this guy. Let's say that we've got the sine of 2x equals the cosine of x. All right, so again, notice we've got two different trig functions. And even worse, we have two different things on the inside. One of them is just x, the other is 2x. Either way, that's a problem. All right, so let's see if we can use identities. What do you think? What might be a good identity to try? How about, is there any identity that even comes to mind here? Okay, so Amber just said the double angle identity, but there's still sine in it. Well, let's just see what we can do. Let's go with the sine of 2x. Double angle identity is 2 sine of x cosine of x. And you're absolutely right that there's still a sine of x. However, we were able to introduce a cosine of x, which is good. So what do the rest of you guys think? Is that beneficial? Was that worth doing? Well, let me remind you of the first example I showed you, where we had 2 different trig functions. I think it was a tangent and a cosine. Because check this out. Let's subtract that cosine over. So we get 2 sine x cosine of x minus cosine of x equals 0. And now that there's a cosine in each of these terms, we can actually factor that out. And factoring is big. If we can factor, so we get factors being multiplied together equaling 0, we're definitely good to go. So from this, we're going to get cosine is equal to 0. And then from the other one, if you just do a little bit of work on it, you're going to get sine of x equals 1/2. You just take 2 sine x minus 1 and set it equal to 0, and then algebra will get you there. Okay, so that double angle identity didn't get rid of the second trig function, but it at least put it into a form that we were able to deal with. All right, so let's get our answers. So cosine equals 0. We know that that happens at pi over 2 and also at 3 pi over 2. So there's the list of all the places that will make cosine 0. And then we also need sine equaling 1/2. There are 2 places where that occurs. It can happen at pi over 6. And then the other one is 5 pi over 6. So we'll go ahead and add our plus 2 pi n to both of those. And there you go. We've got all of our solutions to this original equation. And you really could take any of those angles and or values of x and plug them back in, and you'll see that you get truth. But we used identities to help us get there. Now, let me just give you a tip for these. What you want to look for is when you've got angles, or maybe not angle, the stuff inside the trig functions, if they don't match, you got to do something to them. You got to do something so that they match. So notice what we did was we had a 2x on the inside, and I turned that so that I had just x's on the inside, and they matched what were inside the other thing. That's your best shot. All right, so when you have trig functions with different values inside, try to make them the same using identities. All right, so questions on this one? Other than maybe how the hell are we going to do this on our own when we don't have Bruce leading us? Because the answer to that is practice. The more of these you do, the more you see, the better you'll recognize what identities to use. Okay, so let's do one more where we have mismatched stuff inside and see how an identity is going to take care of us, or help get us where we need to be. All right, so for this one, let's say we've got sine of 2x plus sine of 4x equals sine of 3x. So at first, you might look at this and go, awesome, it's all sines. We already have the same trig functions. But if you look closer, you go, but crap, the stuff inside them's not the same. If these had all been 2x's or 4x's or 3x's, if those had all matched, we would have been happy. Life would have been good. But the problem is they don't all match. All right, so let's see if we can somehow make them match. So what kind of identity do you want to try here? Any ideas or thoughts? How about we just open it up to what are possible identities to use? Okay, so Amber just said double angle identities. Definitely possible, since we've got sine of 2x, sine of 4x. Those things are both even numbers, so we could definitely do that. Mariola Neras just said sum to product. We could definitely try those because we've got two trig functions being added. So we could turn that into a product. What else could we do? There's one more that, there's only one more that would actually be reasonable to do. And that would be to do like a sum of angles. Sum or difference of angles. Like look at this one with the sine of 3x. We could make that say 2x plus x or 4x minus x or something like that to try to do our thing. But I'm going to suggest we try sum to product. Let's just see what happens if we do sum to product on this left-hand side. Okay, so sum to product. Let's go look at that one where we have sine plus sine. So what we see from that identity is we're going to get 2 times the sine of those two angles added together divided by 2. And then we're going to multiply that by cosine of the difference in the two angles divided by 2. And remember, since it's sine plus sine, since we can commute that, you can always just do whichever one you want first. So I always do the subtraction with the bigger one first, so I don't have to worry about negative. So let's simplify this. We're going to get 6x over 2, which is 3x. And then the other one, we're going to get 2x over 2, which is 1x. Okay, so there was sum to product. So what do you guys think? Was that worth doing? So Williams gave me a thumbs up. I think so. And here's why. Because now I actually do have a couple of things that match up, which is definitely a good sign. Those are the same terms. And because of that, I can actually do some algebra now. Let me subtract that sine of 3x. So we have sine 3x times cosine of x now minus sine of 3x, that equals 0. And I can now factor that sucker out. So I'm going to get sine of 3x times 2 cosine of x minus 1. So that identity turned it into a form where algebra can help me. Because now that I have factors equaling 0, or product of factors equaling 0, I can take each one of those and set them equal to 0 independently and solve. So really it comes down to now being able to figure out where does sine of 3x equal 0 and where does cosine of x equal 1/2. So before we finish this one off, any questions? And I'm specifically asking because I'm going to need to erase up here. Okay, so let's go ahead and finish solving these. So we've got sine of 3x equals 0. So for that one, let's think about where does sine equal 0? Well, sine. Okay, so errors real quick. So how do I know factor? Okay, so how do I know factor? Because I've done a bajillion of these, right? I've done so many of these that I see what to do. How are you going to notice that it should be factoring? So first of all, it may not be so just off the top of your head that you're like, oh yeah, I absolutely see that's factoring. It'll take a while for you to start seeing it. But what told me here factoring was going to be a good attempt, was that I had the same functions on both sides of the equation, right? When you go back and you look at what we had after we did the sum to product, on the left-hand side, I had sine of 3x and some other stuff. On the right-hand side, I had sine of 3x. And so if you ever have the same thing on both sides, you know that when you move it over, you're now going to be able to factor. So that's one of the things that I know that I do look for to see whether or not factoring is even remotely possible, or let's say remotely beneficial in that situation. But that's what I do when I have more than one trig function. If I have just the same trig function like we saw earlier with like the sine squared plus sine minus 2 or whatever, that one I just know to try factoring because it looks quadratic. There's a squared term and a regular term, right? But in this case, it was strictly because there was a sine of 3x on each side. So does that help kind of explain my thought process? Okay, so how do I know the answer for the factor? Oh, you mean like when I had the 2 cosine of x minus 1 and how I just jumped to cosine of x equals 1/2? Yeah, okay. That, again, is just because I do it in my head. I do the steps in my head, mostly because I've, again, done a bajillion of these. So if you don't see it, that's fine. Just go through the steps. I'll go ahead and show you. Let me jump back to the board. So what I did here is I basically just didn't show the steps because I wanted to save us some time. But really, I just add 1 to both sides. Let me write it up here. So I have 2 cosine of x minus 1 equals 0. So I'll add 1 to both sides. to move that 1. So I have 2 cosine of x equals 1, and then I divide both sides by 2, and that gives me cosine of x equals 1/2. So that's not what you're talking about? Okay, well then I don't know what you're talking about. Okay, so you're saying getting to this step right here. Yeah, okay. Let me rewrite what it looked like ahead of that. So we had 2 sine of 3x cosine of x minus sine of 3 of x equals 0. And going from this to the next, what I did is I saw that there's a sine of 3x in each piece. So that's why I'm going to factor that out. So what I look at is what's left when I pull that out. So if you look at this first term and you go, okay, well, if I take away that sine of 3x, what remains? Well, there's a 2 and a cosine of x. So 2 cosine of x. I look at the other one, and when I pull that sine of 3x, what remains? Well, nothing. But in this case, I'm dividing. And so when you divide and there's nothing left, it means there's really a 1. So that's what I did. I just divided out. Okay, cool. All right. So now that we're here, let's go ahead and get our solution. So we need to start with sine of 3x equaling 0. So again, where does sine equal 0? Well, it equals 0 at 0. So I'm going to have 3x equals 0 plus 2 pi n. But sine of 3x, sine is also equal to 0 at pi. So we're going to have 3x is equal to pi plus 2 pi. So that's where sine is equal to 0. And in this case, we're going to have to divide by 3. So that's going to give us x equals 2 pi n over 3, and x is equal to pi over 3 plus 2 pi n over 3. So that's what's going to make sine of 3x equals 0. So then cosine of x equals 1/2. If we look at our list there, we're going to see that x is equal to pi over 3. And again, plus 2 pi n. And then the other place where cosine is equal to 1/2 is 5 pi over 3. And again, plus 2 pi n. So there is the list of all the possible values that solve the original equation. All right, so if nothing else, hopefully today gave you an idea of why we care about identities. It's not just for the hell of it. Some of it is. Some of it's just to do math for math's sake and to practice doing the algebra and all that with the trig function. But in reality, there are definitely reasons why we care, and solving equations is one of the big ones. All right, so I think we're going to go ahead and call it here. We still have a little bit of time, but not really enough to start going into the next section. So let me just sort of share what's going to be happening in the next couple of days, because things are a little bit different. So Monday, we do not have class. There's no class on Monday. If you come to the Zoom classroom on Monday, You'll be sitting there in the waiting room for a super long time because I will not be coming in there to check it. All right, so we don't have class on Monday, which means our next class is Wednesday, a week from today. On that day, we're going to go ahead and move into the next chapter. I think we're heading into chapter 9, maybe is the number. But we're going to actually start doing trig. We're going to start talking about how we measure triangles. And specifically, we're going to start looking at triangles that aren't right triangles. Because right triangles, you know what to do. You can already solve all of those without any trouble with the tools that we have. But what we're going to look for are what about those that aren't right triangles? Okay, so that's what we're going to be doing in terms of class. But we're also going to have our next quiz. And that quiz is going to cover pretty much identities, specifically the identities from where the exam left off. So it's going to be things like the sum and difference of angles, the double angle, half angle, power reduction, product of sum, all that. So expect on that quiz a couple of, confirm these identities, simplify using the identities, that kind of stuff. Okay. So that's what the quiz is going to be on Wednesday. And we'll do the usual thing where we do it at the end of class. So I'll turn it on Canvas at right around 12:30. And then you'll have the usual kind of time to get it worked out and then uploaded back. Okay. So that's what's going to happen for us. So instead of my usual have a good weekend, I'm going to tell you, hey, have a good week. And we'll meet back again on Wednesday. So any further questions, comments, anything else before we sign off today? I did say the word of the day, Yair, quite a while ago. Let me go ahead and just pause real quick because